Okay, so last time we were talking about these things, sequences, right? And we were trying to come up with formulas. I would give you a sequence, you would try and come up with a formula. We saw that we ran into, some of them were pretty easy. The other ones required a little more thought. We're going to continue with that. And then we're going to get to a new concept with sequences that we haven't talked about yet, which is called finding the limit of a sequence and finding out whether or not that sequence converges or diverges. But before that, we have to look at a little bit of notation. Something new to some of you. You may have never seen this before, but let's say I wanted to take 12 and then multiply it times 11, then multiply that times 10, then multiply that times 9. And I want to keep doing that all the way till I get down to 1. I could write it out like that, or I could use this condensed form of writing that, which is this, to write 12 with an exclamation point behind it. This exclamation in the back is called factorial symbol. And so this would be what we call 12 factorial. 12 factorial is 12 times 11 times 10 times 9, all the way till you get down to 1. And it's a nice condensed notation instead of having to write everything out. And just a real quick sort of application of where factorial might come up. Just take something like a horse race. No, that's a little bit beyond what we want to do. I was going to say like betting on a horse race, but let's take a combination lock. That's a little bit easier to start with. Let's say you had a combo lock that had 3 dials on it, and you could pick numbers here, 0, 1 through 9, right? 0 through 9. Let's say you're going to set a combination, but you don't want any of the numbers to repeat themselves. Like you don't want to have 2 or the number 3 appear twice. Then how many different ways can you pick that first dial? How many options do you have? There's 10 numbers, right? 0 through 9, that's 10 numbers. And then the next dial, if you can't repeat a number, the next dial you only have how many to choose from? 9. Then the next dial would be 8. So 10 times 9 times 8 is how many, if you multiply those together, that's how many different combinations would be possible. So how is that connected to this? Well, if I write 10 times 9 times 8, right? Do you agree that that's 10 times 9 times 8 all the way down to 1 over 7 times 6 times 5 times 4 all the way down to 1? Do you agree that this is the same thing? I know it looks more complicated, but do you agree it's the same? So you'd have 7, 6, 5, 4, 3, 2, 1 over here, and then this 7, 6, 5, 4, 3, 2, 1 would cancel with all of those, and so all that you would have left is this, right? Yes. But you could rewrite this as what? 10 factorial over what? 7 factorial. And so somehow, when it comes to like what we call combinations or permutations, this factorial symbol comes into play a lot. If you've taken a statistics course, you're familiar with factorial. It's used all over the place. We use it here also, all right? So that's just a little brief background on it. So in general, with the factorial, if you write n factorial, we're going to assume here that n is an integer and that it's non-negative. So that means if we're going to define factorial, we need to make sure we all agree that n can only be 0, 1, 2, 3, 4, 5, 6, 7, 8 forever. So the definition of it is you take the n, then you multiply by what? That same value, but take away 1. So you're going to keep stepping down 1 each time. So n minus 1, then you multiply that times n, take away 2 this time, and you keep doing that until you get down to what? 1, right? That's the definition of n factorial. Now that leads to this question then, what is 0 factorial? Well, it turns out that 0 factorial with this definition wouldn't make any sense. Wouldn't make much sense because, well, you would think it would be 0, wouldn't you? You would just think, okay, replace n with 0 and it's going to kill everything off. It doesn't matter. But it turns out that we define n factorial to be 1. And anytime we define something to be a value, instead of using equals, we put a little colon in front of the equals. And the colon in front of the equals means that we are setting a definition. We are defining 0 factorial to be 1. Now, if you look on YouTube, you can probably look up a video. I think there's something called like Math File or something. This guy that does videos, and he tries to explain why 0 factorial is 1. And he does a pretty good job. I'm not going to get into it because it takes a while to develop it. But if you're interested, there's some sort of justification as to why that's true. So these are the two things in boxes are what we need to know to work with factorials, the basic definition of n factorial, and then to remember that 0 factorial is 1. I'll put underneath here n is an element of the set of integers and non-negative integers. So for us in this class, and for a lot of the math classes you would probably ever take, factorial would not be defined unless you plug in an integer. But it does turn out later, if you do take a lot more math, that you can actually define you can define factorial for any number. So you could actually say, what's pi factorial? And it would have a definition, but it's beyond the scope of this class. All right, let's just practice a couple things with the factorial, just to make sure we're comfortable working with it. As a couple of examples, I want to simplify. Take n plus 3 factorial and divide it by n minus 1 factorial. So what is this? It simplifies according to what I'm saying here. Notice that the plus 3 is in parentheses and then the factorial symbol is behind it. So like if I plugged in n is 2 here, right, we would have 5 factorial over 1 factorial, right? Yes? So this operation of adding the 3 and subtracting the 1 would happen before you do the factorial. With that in mind, what I'm going to do is I'm going to start writing out what n plus 3 factorial is. Let's just string it out. N plus 3 factorial means you start out with the first number, which is just itself, n plus 3. You multiply that times what? N plus 2. So what you're doing is you're going to subtract 1 from n plus 3, right? So n plus 3 take away 1 is n plus 2. And then you could do it again, right? Subtract again, and you get what? N plus 1, and then you could subtract again, and you would get n. And you could keep doing this, right? Keep doing it. And I'm gonna continue up there, but let me just kind of look at what the bottom is. The bottom is n minus 1 factorial, so I would do n minus 1 times what's next? N minus 2, and then n minus 3, and I would keep doing that until I get to 1, right? Yes? Now, up top, I stopped at n, but I would need to keep going here, right? So I would need to continue here. What would be the next thing I write? N minus 1, and then times, take away 1 again, n minus 2, and I keep going until I get to 1, right? N minus 3, until I get to 1. Do you see that what's in red up here cancels with what's in blue down here? See? Each factor cancels. So the n minus 1s go, the n minus 2s go, everything else goes, doesn't it? And the only thing that's left are these 4 factors. Understand? So the answer here would be n plus 3 times n plus 2 times n plus 1 times n. And you could multiply that all out. It would be some polynomial, but that's what it is. Any questions? Sure? Okay, I want to do the same problem, but I want to approach it slightly different. The first way I did, I just really wanted you to see where the cancellation is going to happen. But the second approach, what I'm going to do is I'm going to realize that my denominator, n minus 1, is always going to be smaller than n plus 3, right? It's always going to be a smaller number. So I'm going to write out the top, and I'm going to write it like I did earlier, but I'm just going to keep breaking it down until I get to n minus 1. And I think what I'll do is I'll write the n minus 1 in red. Now, technically, I should just keep writing n minus 2, n minus 3, n minus 4, right, all the way to 1. But do you agree that if I just throw a factorial symbol just on this one right here, then that means n minus 1, then n minus 2, then n minus 3? Do you see that? And if I do it that way and then rewrite the denominator and don't do anything to it, just write it down, then these are exactly the same, and they cancel right here without me having to write everything out. That's the way you want to see it. You want to see it as you're trying to get one of the factorials to kind of peel off all the factors until they match and then cancel them out. Cancel, cancel, and then that's the same answer. Here's another example. Which of these is going to be bigger, numerator or denominator? Denominator is going to be bigger, right? Because 2n plus 2 is bigger than 2n minus 1. So this time what I'm going to do is I'm going to start rewriting the denominator and keep breaking it down and reducing it until I get it to look like the numerator. So help me out. Tell me what my first factor would be. What's the first thing I write? 2n plus 2. What would the next one be? 2n plus 1. Because you're just subtracting 1 from 2n plus 2. Take away 1, you get 2n plus 1. What would the next one be? Just 2n, right? And the next one? 2n minus 1. Am I going to go again for the next one? No, because this 2n minus 1 matches this right here, doesn't it? So instead of writing everything out the rest of the way, I'm going to throw my factorial symbol right at the end of this one. And that represents taking that and continuing it. And then rewrite the one on top. And cancel, and you're done. So what's the answer here? 1 over, yeah, don't forget your stuff was in denominator there. 1 over 2n plus 2 times 2n plus 1 times 2n. Box it up, we're done. We good? Any questions? All right, let's move on. We're still in the same section, 8.1. I think I lost track of my notes, like my numbering system, but like I said, I'm delirious, so I'm just going to keep talking. I'm not even going to worry about numbering things right now. So we need to define now what's called the limit of a sequence. We were coming up with formulas, right? Like I gave you a sequence and we tried to come up with a formula. If I gave you a formula, then you could write out the sequence, couldn't you? You just start plugging in 1, then 2, then 3, and that's easy way to do it if someone gives you the formula. The question becomes, does this sequence of numbers actually approach something? Does it get closer and closer to something? And so for a visual of what I'm talking about, let me bring up this. Take a look at this sequence. This is the sequence. Come on, get over there. This sequence right here is the sequence a sub n equals n squared over 1 plus n squared. I'm just giving you an example. So what happens when you plug in 1 to this? You get 1/2, right? So check this out. If you go in here and you plug in 1, you get 1/2. So that black dot is the first number in my sequence, right? Then I plug in 2, and when I plug in 2, it spits out whatever you get here, 2 squared, 4 over 5, so 4/5, which is here. Is that right? 4/5, okay. And then the next one you plug in 3. So the red here, ignore the red. The red is just trying to show you, look, this black sequence of dots is behaving kind of like that red graph, isn't it? And as I go further and further out, come on. I thought I could go further out. Oh, number of points, there we go. So if I go further out, you can see that it looks like we have some sort of what we would refer to as a limit. It's getting closer and closer to something, isn't it? Like it's not taking off to infinity. It's not oscillating back and forth. It's actually headed to something. And so the question would become, what is the limit of that sequence? What is it approaching? It may not ever get to it, but it may approach it, just like in Cal 1. So that's the idea behind the limit. And so we need to define it first. So the definition of a sequence, or definition of limit of a sequence is, so definition, if we're given a sequence a sub n, if we write lim, you thought that limit was gone, right? And goes to infinity of a sub n equals L. So if we write this down, I'm going to tell you what it means in a second, but this is what we're saying is we're letting n go to infinity. That means we're looking at the sequence and we're trying to look at the numbers in the sequence as we keep on going further and further and further out, right? If we say that that limit is equal to L, where L is a number, then we mean by this, as n gets large, a sub n gets closer and closer to L. And now I'm using very, very loose terminology here. When we say close, what do we mean? I know we've had that discussion right before about what does it mean to be close. There's a very precise definition of this limit, but I think we'll reserve that for math majors and let them deal with the whole delta epsilon definition of a limit. Okay, for us in this class, we just want to have the idea that as n gets big, this thing's getting close to something. Now, that's what we mean. This is the notation we use, okay, to say that that's what's happening, but there's an alternative notation. So another notation, we write that's just a cleaner notation right there. What we mean by that is kind of what it says, right? What it represents. A sub n is going towards L. That's the definition. Limit n goes to infinity. This thing gets close to L. Well, that's what that little arrow between them means. Okay, so if you see this, just remember it means this. Now, if the limit exists, is a number. So that's what I'm going to mean by the limit exists. Remember in Cal 1, sometimes limits didn't exist. So we may run into a situation where the limit doesn't exist. So we say that if the limit does exist, if it actually turns out to be a number, then we say the sequence converges. So a convergent sequence is a sequence that when you actually go out to infinity in the sequence, it's approaching a finite number. It's getting closer and closer to some finite number. If the limit doesn't exist, what are we going to say? So otherwise, we say the sequence diverges. All right? So what we're going to do for, I don't know how long it's going to take us, but for quite a few problems now. So we're going to take a look at some sequences. We're going to try and figure out if they converge or diverge. That's what we're going to do. Now on page 429 of your book, let me just double check that page to make sure it's right. By the way, I have my phone on. If it rings, I'm just going to walk outside in case something came up with my daughter. On page 429, that is correct. There's a box, and it's called the limit laws. I'll ask you to go look at these limit laws. They are very, very similar to the limit laws that you had in Cal 1, which meant that, like, if you were going to do the limit of a sum, you could break it up and do the limit of each one. If you want to do the limit of a product, you break them up and just do the limit of each one and then multiply the answer. So all the rules are still the same for limits as they were in Cal 1, which is a good thing. But I'm not going to go through all of them. All right, just know that they're there. Please review those when you have some time. Let's see, 12, 13. All right, so let's try some examples. Find the limit as n goes to infinity of the sequence n over n plus 1. Now, you don't have to do this, but you could, if you want, start writing out the individual terms of the sequence. So like if you plug in 1, you'd get 1/2, and then the next one would be 2/3, and then 3/4, and then 4/5, 5/6, and so on and so forth forever, right? What does it look like these are getting closer and closer to? We're getting closer to 1, right? Think about 100, right? You'd be 100 over 101. That's very close to 1. But we need to show it somehow. So how are we going to show that it's 1 algebraically? So when n goes to infinity, what does the top do? Goes to infinity. When the bottom goes to infinity, infinity plus 1, still infinite, right? So we have this form of a limit where you have infinity over infinity. I'm not going to let anyone fall into this trap, because I was going to ask you, what do you do when you have infinity over infinity? And someone was probably going to say L'Hopital's rule, right? Someone was probably going to say that, maybe? Here's the problem with L'Hopital's rule. L'Hopital's rule said you take the derivative of the top and bottom, right? That's what L'Hopital said. But in order to take a derivative, if you remember from Cal 1, when you had a function, right? When you talked about a derivative, you were trying to find the slope of this tangent line. What you did to find the derivative is you took a limit, didn't you? You took the limit. You may remember this definition because it was very painful in Cal 1 for quite some time. You do limit, h goes to 0, f of x plus h minus f of x all over h. Remember this? This is the difference quotient, and then you put the limit in front, and that's the definition of the derivative. Here's the problem why we're going to run into an issue and not be able to use L'Hopital's rule on this. The issue is that when you take this limit and you let h go to 0, what you're doing is you're approaching that point from both sides. You're approaching it from both sides, and you're trying to figure out what's going on with that tangent line. And so don't you have to have something on each side of that dot in order to be able to do that? And our sequences don't have that, do they? They're just points, points, points. So if we go to one of the points and try and come in from both sides, there's nothing arbitrarily close to each side. There's big gaps between each point. So L'Hopital's rule will not apply to a sequence. Understand? Now we're going to have a workaround because there's a theorem that's going to allow us to use L'Hopital, but we have to be aware that sequences don't behave like functions, so the things that we use for functions cannot just automatically be used for sequences. Okay, so there still is a way to do this. Let's see if you remember this. I would use L'Hopital's rule if I could, but since I can't, I'm going to use this. I'm going to divide or multiply the top and bottom by 1 over n. Right? What I'm doing is, the reason I chose 1 over n is I'm going to try and turn the highest power of n in the denominator into a 1. So if I divide n by n, then it'll become a 1, won't it? If this had been an n squared, I would have done 1 over n squared. So then multiply those through, and let's see what we get. On the top, you get 1, don't you? On the bottom, when you distribute to each of those, you get 1 plus, what is that, 1 over n? Distributing that through. And now what happens when you let n go to infinity? What happens here? Yeah, this guy right here goes to 0. And that doesn't change. We're not using L'Hopital rule there. We're just saying, hey, look, you have a fixed number, 1, and the denominator's getting huge. That thing's going to squish down to nothing. And so you just get 1 over 1 plus nothing, which is just going to be 1. That's what we said it looked like it was going to, right? Yeah? So that's the way you could do that problem without using L'Hopital's rule. So let me give you another one, see if we can get the next one. That was just to get us thinking. How about limit n goes to infinity of natural log n over n? What do you think here? What's happening up top? What does natural log of n do as n gets bigger? So that's just asking you, what does the natural log look like? So where's it headed? Hello? Infinity, thank you. And where does the bottom head? Infinity, right? So you have infinity over infinity. So you're like waiting to pull out the L'Hopital rule on this, but you can't. So you try that thing, that 1 over n thing. If you do that, you're going nowhere also. Look, if I do 1 over n here, 1 over n here, on the bottom I get a what? 1, but on the top, what do I get? Natural log n over, and I'm right back where I was, right? So that didn't do anything to help me. So that's not going to work. All right, so we're kind of stumped here, maybe, right? And this is where the theorem comes into play. All right, we have a theorem. Let's see if the book has a number on it. Yeah, it's on page 428. It's theorem 3. 428. All right, it says, the book says it a certain way. I'm going to say it another way that I hope makes more sense. All right. If f of x, limit as x goes to infinity of f of x equals L, where x is an element of the real numbers, then the limit as n goes to infinity of f of n will also equal L, where n is an integer. Well, we'll put this, sorry. I'm trying to do double struct n. Having trouble. Y'all know what the double struct R is? Real numbers, okay? Natural numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, forever. So what this theorem is saying is, if you have a function that has as x goes to infinity, if that function is approaching L, where x is any number, real number, then if you just restrict yourself to just the natural numbers, that function on just the natural numbers should also go to L. And the picture for this is basically this one right here. So let me back this out. And let me change this up here. Change it to log n over n. Let's see what happens. It's having a little bit of trouble with 0 there. There we go. So this is the graph in red of the natural log of the natural log of x over x. Right? It's a nice continuous function, nice and smooth. Damn it, come on. I'm looking for my dots. Do you all see my dots? I don't see my dots anywhere. Maybe the size needs to be bigger. There they are. Okay. Thank you. Y'all are gonna have to help me today because I'm struggling. But okay, so if the function does something on all the real numbers, the dots have to follow it, right? So this theorem I think is pretty obvious. Would you agree? So whatever the red function does, the black dots do. Which means that we can use L'Hopital's rule. But we couldn't do it just because we've used it in the past. We have to understand the distinction between a sequence and a function. The sequence is defined on just those integers. The function is defined everywhere. They're completely different animals. So with this theorem in mind, now let's revisit this problem up here. What I'm going to do is I'm going to convert it first. I'm going to say let f of x equal natural log x over x. Right? So if I take the limit now as x goes to infinity of natural log x over x, and use L'Hopital's rule now, because it was infinity over infinity, I get limit x goes to infinity. What is the derivative of the top? Derivative of the top. 1 over x, derivative of bottom, 1. And so what's this going to turn into as x goes to infinity? 0. And by theorem 3, I'll just put theorem 3, this implies that a sub n equals natural log n over n will also go to 0. See, I'm using that arrow this time, the arrow meaning the same thing as the limit. So the theorem says if the function behaves a certain way on all the real numbers, then it's going to behave that way on the natural numbers. So do you see the distinction between me using an x versus me using the n? When I use the x, I'm implying that that's a real number. When I use an n, it's understood that it's 1, 2, 3, 4, 5, 6, 7, 8, 9. And if you ever take more math, and you ever get to a class called complex analysis or complex variables, we use a z for our variable to represent that it's not a real number, it's not a natural number, it's actually a complex number. So you're allowed to like throw imaginary numbers in there. So we use a different variable to kind of remind us that we're restricted to a different domain. Okay, so that right there, this theorem really opens up what we can actually find limits of, because now you can use L'Hopital's rule, right? Another example, what's the limit as n goes to infinity of, let's do this one. -1 to the n over n. Take a look at it first. I'll just type it into the calculator or to the computer. It was -1 to the n, then divide that by n. Interesting. So what happens when you plug in 1 to this? What happens when you plug in 1? You get -1. So look, when I plug in 1, I don't think it's on my graph here. Where is it? There it is. So when I plug in 1, which is right here, I get -1. When I plug in 2, I get what? This time, the top's going to be positive, right? Because the -1 to the n is making it an alternating positive negative, or actually it's going to start negative, then positive. And then, so I plugged in 2, I got a 1 on top. Plug in 2, I get, plug in 2, I get 2 on bottom. So I had -1, then I have 1/2. The next one's going to be -1/3, then +1/4, right? -1/5, positive. So it's alternating back and forth between positive and negative numbers, but these numbers are getting smaller, right? So as I go, it looks like the limit is what? 0, right? But you cannot use L'Hopital's rule. You can't do it. L'Hopital only worked when you had what? 0 over 0 or infinity over infinity, right? This is neither one of those. The top is not going to infinity. The top is going back and forth between -1 and 1. The bottom is going to infinity. So how are we going to get around this to actually come up with that conclusion without being able to use L'Hopital's rule? I think you might be able to just reason, within your own mind that the numerator here is what we would consider to be bounded. Do you agree the numerator is bounded? I mean, the biggest it's going to be is 1. Smallest it's going to be is -1. So it's always between those two values. Actually, it's one or the other. And then the bottom is headed to what? infinity. And so no matter what, worst case scenario, the top is 1, and we're dividing it by a huge number. That should be tiny. Or the other extreme would be the top is -1. We divide it by a huge number. That's going to be a very small negative number. Either case, they're both getting smaller, getting closer to 0. So thinking through it, it appears that this would be 0. But we will use a theorem in order to reassert what our minds are telling us it should be. So this is going to be theorem 6 on page 429. Look, I mean, I never write the word page. I'm so tired. All right. So if the limit as n goes to infinity of the absolute value of n equals 0, then the limit as n goes to infinity of a sub n equals 0. This theorem is very useful when we're looking at alternating sequences, because what the theorem allows us to do is it allows us to ignore the alternating part of it, because we're going to take an absolute value. If that absolute value of that sequence goes to 0, then we can conclude the original sequence went to 0. So let's revisit this problem right here. Let's get the same conclusion, but let's use this theorem to do it properly. So limit n goes to infinity of -1 to the n over n. So by theorem 6, what I'm going to do is I'm going to take the limit as n goes to infinity of the absolute value of that, and that equals the limit as n goes to infinity of just 1 over n. Now, why can I turn the -1 to the n into a 1? Because no matter what it turns out to be, right, I'm going to take the absolute value, and the absolute value of 1 or -1 is 1. So the top is just going to become 1. Why do I take the absolute value of n and get n? It's just n, right? Remember, n is a positive number, right? So the absolute value of it should be itself. So this is just going to reduce to be this. And this limit is a very, very basic one from Cal 1, right? You just have fixed number over infinity. That's going to 0. So since the absolute value of the sequence went to 0, what does that tell us? Therefore, -1 to the n over n goes to 0, right? So I didn't mention this, now I will. Chapter 8, all right? A lot of what is going to be on the test that you'll be graded over is going to be not can you get the answer, but the actual work leading to the answer. Because we're going to do these things called series convergence tests. And so what you'll do is you'll be given a problem, you're going to be asked, does this thing converge or diverge? And you actually have to go through this logical process to figure out whether or not it does or doesn't. And that's what I'm grading. I'm grading the process of your thinking and whether or not you're drawing correct conclusions or if you're just kind of like guessing at it. So you see how I wrote this down and I put by theorem 6 and I actually kind of explained in some way what I was doing? That's what you're going to have to get used to doing. Writing down what it is you're doing. Not just like you know what you're doing and you're just writing it down. You need to be able to explain it to a reader, which would be me. Understand? So work on that, please. All right, let's do another one. We said last time we would see how far we got. I think everything up to 8.2, I mean 8.1 will be, but not on 8, not 8.2. So this section would be. This section would be, yes. All right. Next problem. Okay, how about this? Limit n goes to infinity. Yeah. -1 to the n times n over n plus 1. So how do you want to approach this? Do you want to write out some of the sequence first and see if you can find behavior just to start, or do you just want to look at it and, like, you know, just plug in and say what's happening? I mean, what do you want to do? You just want me to show you the way I would do it, or what's happening to this piece right here? Tell me what's happening to this. Just switching signs. That's all that's doing, switching your signs. Okay, what's happening to this? Going to infinity. All right, what's happening here? Infinity. So we almost have kind of like an infinity over infinity, except that the top is actually switching positive and negative infinity, right? Like it's going back and forth. So how about the theorem we just had? I like this idea. Let's see, I think you're saying let's do this, and then say times, and then just the n. And because of the limit laws, you could actually split it into a separate one like this. Okay? This would be perfectly fine. The problem is your conclusion is going to be inconclusive. Because this is going to what? We just said, you take the absolute value of that, that's basically going to go to what? 0, so we know this is going to go to 0. What's this going to? Infinity. And you get 0 times infinity, which is indeterminate form. So that would work, but your conclusion wouldn't tell you anything. So yeah, that would be one approach. But then we go, nah, maybe not. So how about the absolute value? I'm going to show you this because you'll see. What's the limit as n goes to infinity of the absolute value of this? So how does the absolute value around that whole thing change the problem? I mean, what's the only thing that changes now? That -1 to the n, it's gone, right? It's like a 1 now. That's the beauty of the absolute value on an alternating sequence, is that the absolute value of it just makes you wipe the -1 to the n out completely. So we're really just looking at n over n plus 1, aren't we? And what is this? Didn't we do that problem already? What did we say that was equal to? 1. Okay. So what? So does theorem 6 tell us that the answer is 1? Come on, y'all. Look, I'm on, like I said, a few hours of sleep. I'm up here, I'm trying. I need y'all to at least try and answer me. My question is, does theorem 6 tell us that the answer to this up here is 1? What does theorem 6 say? If this limit of the absolute value goes to 0, then the original sequence goes to 0. Does it say what happens when the absolute value goes to something other than 0? No. Which means that this doesn't tell us anything at all. So I'm showing you this because you have to be careful with what the theorem allows you. The theorem says if that were a 0 right here, then your answer would be yes, it's 0. But if it's something other than 0, the theorem fails to tell you anything. Understand? Theorem 6. Theorem 6. Because I took the absolute value. Theorem 6 is the one that involves the absolute value. So Theorem 6, conditions aren't met. In other words, the limit of the sequence absolute value does not go to 0, right? I'm just trying to reiterate. You wouldn't need to write this down, but if you're going back and looking at your notes, why is it that I can't use Theorem 6 here? Because the condition that it had to go to 0 isn't met, right? So for this one, I think what we're going to have to do is just get this one by writing out the terms and coming to a conclusion, just a logical conclusion. There's not going to be any algebra really that we are going to do for this. Let's start writing them out. The sequence itself. We plug in 1, we get what? -1/2. Next one would be 2/3. Next one, -3/4, right? Next one, 4/5. Next one, -5/6, ... like that. If we were to draw this out, it would look like this. Let's say this is -1 right here, and this is +1. First one would be -1/2. The next one would be what? +2/3. The next one would be -3/4. The next one would be +4/5. And then, so what's happening is that you actually have almost like two asymptotes, don't you? The top ones that are positive are getting closer and closer to that. The negative ones are getting closer and closer to that, -1. And so can you say that the sequence is headed to one number? No, you can't. It's headed to two different numbers, which means the limit does not exist. Are we good on that? Questions? So up here, the answer would be does not exist. DNE does not exist. Limit does not exist. Therefore, it diverges. I'll put up here the limit does not exist, therefore it diverges. That is a divergent sequence. All right, how about this? Limit n goes to infinity of (2n plus 1 factorial over 2n plus 3 factorial. What happens as n goes to infinity here? What is infinity factorial? I mean, that doesn't really make a whole lot of sense, but as this number gets bigger, isn't that a huge number? I mean, think of it, if you plug 100 in here, it's 100 times 99 times 98. That's a huge number. So the top's getting huge, right? Bottom's getting huge. Infinity over infinity. You start thinking maybe L'Hopital, but you can't. Why can't you use L'Hopital here? Factorial is only defined on the integers, right? So we said that there's a workaround. Theorem 3 said if you could draw the function out, and whatever it does, the dots do also, right? But factorials are not continuous functions. They only are represented as dots. So there is no derivative that you could ever take, right? No one here knows what the derivative of factorial is, right? I mean, it's because you didn't talk about it, right, ever? And there is none. Doesn't make sense to talk about it. So how are we going to do the workaround? Just simplify it first, right? We simplify it. Which one's bigger? The bottom one. So we're going to start peeling away the bottom one. And when I peel away the bottom one, I start with 2n plus 3. Then next one is 2n plus 2. And the next one is 2n plus, oh, that's it right there, right? 2n plus 1. And then I factorial after that, so I don't have to keep writing it out. Cancel. Two n plus 3 times 2n plus 2. What does that go to? Goes to 0. You've got a fixed number over infinity. So that limit, that sequence converges to 0. All right, next one. Limit n goes to infinity of n factorial over n raised to the n. Things are starting to get a little bit interesting here. As we really, n to the n is a function that you probably didn't see even a lot of in Cal 1, like a function x to the x. Like, probably never really looked at a function like that. So n to the n is not, I guess, something that we're familiar with. And then n factorial is kind of new. So let's just talk about the behavior. N goes to infinity, top's going where? Infinity. Okay, and then what's infinity to the infinity? Infinity, I guess, right? So we have that. We think in L'Hopital. We see the factorial. Forget it, right? Forget it. So how can we do this? This one's a little more involved. So let's first write this out. I'm going to show you this. This is kind of one of those problems where I show you it the first time you see it. You're like, okay, now I know I can do that from now on. Limit n goes to infinity. I'm going to write out what these are. N factorial is n times n minus 1 times n minus 2 times dot, 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 all the way till I get to 1, right? Times 1. Over, what's n to the n? N times n times n times n until I get to n, right? It's n times n times n how many times? N times, right? Oh. Do you agree? That's what it means? So let's do something I think is pretty obvious right away. Is those n's cancel, don't they? Yes? Those n's cancel. And let me rewrite this. I'm going to kind of turn it around. Trying to think of how I want to write it. I know that that looks kind of weird to write it this way, but do you agree that this is the same thing as this? It's written backwards. 1 over n is here. Yes? And then the next thing in front of this would have been a 2, and that would have been over n, and that's here, and then a 3 over n, then a 4 over n, and I'm going backwards until I get out to n minus 1. Yes? Agreed? All right. Let's focus all of our attention right now on just that. I'm going to write that down by itself. Forget that it's in a limit. And I'm going to write an inequality, and I want you to tell me whether or not you agree with this inequality or not. 0 is less than or equal to 1 over n times 2 over n times 3 over n times 4 over n times all the way till I get out to n minus 1 over n. But that's less than 1 over n. Do you agree with this or not? And I'll throw one more hint into this, times 1. So let's first establish this inequality. This is a positive number, right? Every one of these are positive numbers. So it's got to be greater than or equal to 0, yes? Okay. Now, I had split this 1 over n off the front like this just to stress this right here. These two parts match, right? So 1 over n is equal to 1 over n. So I'm just really asking you to compare this to this. Do you agree that 1 is bigger than this? Or, you know what? I should change that. Let's change this to 2. See if you agree with this. This will be easier to do. What's the smallest that n could be? 1, right? So if this was 1, right, what would this be? 2? 2? I mean, what, 2? 3 halves? 4? If you multiply those together, is that less than 2? You sure? If n is 1, what's this number? Okay, if n is 1, this is 2. Then times 3 halves times 4 halves, right? Times 5 halves. Are we agreeing or not? Wait, say again? 1, 1? Oh, if I said n was 1, okay. Well, that makes it even easier. Is this number right here in yellow, is this number right here smaller than 2? No, it's not, is it? Not when n is 1. What about when n is 2? Then that would be a 1. This would be what? 3 halves, then this would be 2. So that's not either, right? Understand? So I'm trying to see whether or not we can say that this inequality is true or not. Because what we're trying to set up is this. What is referred to as the squeeze theorem. Do y'all remember squeeze theorem from Cal 1? Squeeze theorem said that if you have a function that's stuck between two other functions, if the two other functions go to the same place when you take the limit, then the one in the middle has to also go to the same place. So if that, again, is something you don't recall from Cal 1, you can go reference that. We are trying to do this. We're trying to take a sequence I'll call A sub n. We're trying to squeeze it between two other sequences, which I'll call B sub n and C sub n. So if we can set up an inequality that looks like this, then the squeeze theorem says if if B sub n goes to L and C sub n goes to L, the conclusion is what? If this guy, when you take the limit, as you let n go to infinity, if that goes to L and this one also goes to L, since this one has to be between the two, it's also got to go to L. Yes? So what do y'all think? I'm not, well, this makes sense, right? But does this up here, is this inequality true? Because I'm trying to squeeze it. Notice that over here, what would this go to? What would this go to if I let n go to infinity? What would it go to? 0, and then this side is what? 0, and then that would force this to be 0. But this has to be shown that that's true. And it's not. I'm not convinced of it because I plugged in 1, right? When I plugged in 1, what did you get? Huge number? This inequality has to always hold. So the arrangement of things, just see how I rearranged it in this way? Somehow that's not allowing this inequality to do what I want it to do. So what I'm going to do is go back to this and try and rearrange it another way and try and force the squeeze theorem to work. So take this right here, and I've got to go to a new page, and let's try and rewrite it slightly different. Where's my new page? Right there. Okay, so we're taking, what was it, n times n minus 1 times n minus 2 all the way down to 1 over n, all the way down to n, and rearrange it, right? So what about this? 1 over n, and then 2 over n, times 3 over n, times 4 over n, all the way out to n over n, right? Is that the same thing we just had? 2 over n, 3 over n, 4 over n, all the way out to n. I said n minus 1 over n. Why did I cancel these n's, right? Yes? So we agreed, I think we agreed on this one, that when n was 1, it didn't work, right? So what could I use over here that would be an upper bound? I'm having trouble with this. My brain is completely fried right now. Which doesn't help you when you're trying to learn it. So we need to convince ourselves that this right here is less than 1. And we can do this. We said it doesn't work when n is 1, right? So then it doesn't work when n is 2. When n is 3, does it work? The thing is, these keep going up, right? But look at this last term right here. Look at this last one. Isn't this term, that last one right there, would you agree that that's always less than 1? Yes? That's less than 1? So is the one before it less than 1? Well, that's the one on this side, the n over n. Are you talking about this one right here? Yeah, so the one right before it is n minus 1 over n, right? I agree this one is 1. This has got to be smaller than 1. Hmm. Well, we are letting n go to infinity, right? We are letting n go to infinity, right? That we want to limit. So we know that this one right here would go to what? 0. This one would go to 0. This one would go to 0. But the problem is when you get out to the end here, you know, you keep going out. Each of these are getting closer and closer to what? I mean, they're getting closer to 0, but the top's getting bigger, isn't it? And the bottom's getting bigger? Or getting closer to n? All right, look. Look, let's just stop with this, please, because I don't think there's any way I'm gonna be able to recover from this right now. I think we'd have to just start it over, and I just have to like take a deep breath, and I don't really want to right now. So I'm just gonna leave this open for now, all right? And I'll come back to it and clarify it, all right? If y'all could give me that, I'd appreciate it. We need to use some sort of squeeze theorem on this to make it work. Okay? Here? That goes to 0. As n gets bigger, that goes to 0. If you go back up to this one. Yes. Look, here's the problem. The problem is that we can't fix n. You can't fix it because we're taking a limit as n goes to infinity. So what's happening is that this is getting longer, isn't it? You're getting more and more of those. And this is getting longer right here. If we actually just fix an n, of course, we can figure out what it is. But we're trying to figure out what happens as we let n get larger, which means that those things, the denominator just keeps getting bigger, more factors of n, and this has more factors in it also. I'm sorry? Yeah. So let's just come back to it, okay? Because I think I've already confused everyone enough, so I think it'd be best if we just move on. All right. All right. We are going to look at one important sequence. I mean, I'm just amazed at how you hear about these like torture tests that people are put through where they're like kept up for hours and hours and days, and how much of an impact it has on them. Like, I can see it now. Like that should be not an issue at all for me right now to show y'all that. And I mean, my brain just does not want to rationalize it, period. Well, I don't know. It was different back then. I don't know. It was way different. You're right. because there were many sleepless nights. But I think it's a combination of that and the stress of your daughter being hooked up to IVs and like you sitting there going, what is going to happen, and just stress and all that too. Yeah, that's why I haven't slept in like 2 days. No, I think she's okay. But anyways, all right, an important sequence that we should be aware of. A sub n equals r to the n, where r is a real number. No, we want it to be a positive. Sorry, r is greater than 0, and r is a real number. You don't know how much fun you've missed already. Yeah, it's been great. So some examples of this sequence would be something like the sequence pi to the n, the sequence 1/2 to the n. Anytime you put a positive number in the base, raise it to the n, what does the sequence do? So what do you think this goes to? How do you think this sequence behaves? What does r sub n go to? Or r to the n go to? That's the question. Won't it depend on what the base is? Like if the base is a number like pi to bigger and bigger powers is going to get bigger, isn't it? But if it's a number like 1/2, 1/2 to bigger and bigger powers can get smaller. So the way to determine what r converges to will depend solely on what r is. And so we have two different scenarios. It'll go to infinity if r is greater than or equal to 1, and it will go to 0 if r is between 0 and 1. And remember, if it goes to infinity, we would say it diverges. All right? It would diverge. So just keep that in mind. We'll use that as we proceed. Anytime we see something like this, oh, hey, look, what does that go to as n goes to infinity? What is it? That one goes to 0. This one goes to infinity, so it diverges. Yes? Okay. All right, some definitions. Increasing sequences. What is an increasing sequence? If a sub n is less than or equal to, or less than, sorry, a sub n plus 1 for all n. That upside down capital A means for all. For all n. So an increasing sequence is one where the nth term is always smaller than the next term. So the first term is smaller than the second one, which is smaller than the third one, which is smaller than the fourth one. And so when you look at it, reading it from left to right, these dots start going up, okay? They go up. That's what an increasing sequence looks like. What about a decreasing sequence? What's the only thing you change? Where you at? What would you change to make it decreasing? Just flip the inequality over, right? Flip the inequality. Now it says that the nth term of the sequence is actually bigger than the next one, which is bigger than the next one, which is bigger than the next one. So it looks like steps going down instead of going up. In either case, all right, in either case, increasing or decreasing, doesn't matter. These are both considered monotonic sequences. So if I say, hey, the sequence is monotonic, that means it's either going up or going down, increasing or decreasing, right? So monotonic is a more vague description. It's like, and then these are the two conditions you can have. Now, not every sequence has to be increasing or decreasing. It's not one or the other. You can have neither one. Think of like the sine function, right? Doesn't increase or decrease. It keeps changing. All right. The next idea is what it means for a sequence to be bounded above. Yes, this is all 8-1. So what does it mean for a sequence to be bounded above? If capital E backwards, there exists a capital M such that A sub n is less than capital M for all n. Okay, see if you can read that. If there exists a capital M such that A sub n is less than capital M for all n, then we say it's bounded above. Now M here, right? This right here is just a number. So think of it as like the ceiling. There's a ceiling. You've got the sequence, it's always below it. So if there's an M where the sequence is always below that M, below that ceiling, then we say that the sequence is bounded above. And then what about the other way? Bounded below? If there exists a little m such that the inequality the other way, A sub n is greater than little m for all n, then we'd say it's bounded below. So this would be like a floor. It would be something that's always below the sequence. Do you all understand this? We're good? All right, so now with that, we say if A sub n is bounded above and below, okay, above and below, we call it, or we say, A sub n is bounded. This can be a little tricky with the language here. Bounded above means there's a number that is always above the sequence. Bounded below means there's always a number below the sequence, right? If you say a sequence is bounded, you're not saying it's bounded above or bounded below. You're saying it's both. You would think that if it's bounded above, that's enough for you to say, oh yeah, it's a bounded sequence. No, to say it's bounded, it has to be bounded on both top and bottom. That means it's always between two lines, two horizontal lines. And from that, we get what's called, from all this, we get a new theorem. See if they, yeah, it's theorem 11 in the book. It's called the monotonic bounded sequence theorem. Huh? Do you need to memorize it? You need to know it. Yeah, I guess so. I don't know if you want to call it memorize, but you need to know what it's saying and what it. I won't tell you like state the monotonic bounded sequence theorem. I won't tell you to state it, but you're going to need to know how to use it, which means you're going to need to know how to reference it. So you'll need to know it well enough to. It's in the book? No. Mm-mm. Mm-mm. So it says here, this is what the theorem says. Every bounded monotonic sequence what? Every bounded monotonic sequence blank. What do you think? Converges. Okay, so let's see. Why does this theorem make sense? You've got a sequence, right? It's a bunch of dots in here. I'm about to draw them. But here are the conditions. It's bounded, which means that it's got to live between these two, right? So what it means to say bounded? This is saying every bounded monotonic. What does monotonic mean? It's either increasing or decreasing. So try and draw me an increasing sequence in here that doesn't converge. So I'm going to start drawing a sequence. Here it is. There's my first dot. The next one has to be above it, right? Or equal to it, but can't be below it. And then I keep going to the right, and I either have to keep going up or I need to flatten out, right? One or the other. And so as I keep moving up, if I'm not allowed to turn back down, that means eventually I have to flatten out, don't I? Because I can't ever pass up that green line. So eventually I'm going to converge to something. And if you did it the other way, it would work the same way. All right, so look at this problem here. Is A sub n equals n plus 1 over n bounded? Is it monotonic? Two questions. Is it bounded? Is it monotonic? So let's start with bounded. What does it mean for me to figure out if a sequence is bounded? I have to find a number that's always bigger than the sequence, and I have to find a number that's always smaller, right? So let's just look at it and see if we can just kind of guess as to what might work. And maybe it'll be helpful for us to write out a few of the terms. Like plug in 1, you get 1 plus a half. What's that, 3 halves? Plug in 2, what do you get? Oh, wait, I said 1. Plug in 1. Plug in 1, you get what? 2, thank you. Plug in 2, you get 2 plus 1 half, which is 5 halves. You plug in 3, you get 3 plus a third, which is 10 thirds. Okay, that should be good. Can somebody give me a lower bound on this sequence? 1? Y'all happy with 1? So now you need to show it's true. That's a good, I'd say that's a good conjecture, that 1 is a lower bound. So my claim here is that little m equals 1. This is going to be a lower bound. If that's my claim, I need to prove it. So I just need to show that 1 is always smaller than n plus 1 over n. Isn't that what I have to show? Prove to me that this is always true. How are you going to prove to me that that's always true? You have to be careful. You can't just start plugging numbers in. And the reason why is because you would have to do that for every number. and be able to convince someone that it works for every number. Here's what I think would have been a better, an easier way to make this claim. Although this is perfectly fine as far as, you could probably convince someone eventually, right? I mean, look at this number right here. Oh, lost it. Look at this number right here. That number, what's the smallest it can be? 1. And then 1 over anything is going to be a positive number, right? 1 over n is going to be positive. So if you take 1 and you add a little bit more to it, it's got to be bigger than 1, right? So I think you could almost convince someone just by writing that down. But we want to do something that's going to be a little more algebraic. So how about this? How about changing it to 0? I mean, is 0 a lower bound? I mean, if 1 was smaller than it, then sure as hell 0 could be, right? This is just a little bit easier to work with algebraically. Just move this to the other side, right? Just move that to the other side. Negative 1 over n, is that less than n? Absolutely. Look, n is always a positive number, right? So negative 1 over n is always a negative number. So the left side's negative, the right side's positive. That inequality is true all the time. So I could just put a check mark on that and say, yeah, I'm okay with that. Understood? Now you need to find an upper bound. Capital M. What about an upper bound? Is it? What happens as n goes to infinity? That becomes infinite, right? 1 over infinity is going to go to 0. So isn't this thing just going to infinity? So how are you ever going to have an upper bound? You're not going to. So I'm going to say not bounded above since what? I need to justify my conclusion here. Since limit as n goes to infinity of n plus 1 over n is what? Infinite. There's no way I can find a number and say that number is bigger than my sequence all the time, because if I go far enough out in my sequence, I'm going to pass it up. All right, so the question here, is it bounded? No. It was bounded below, but not above. So the answer to this is no. Is it monotonic? What does it mean to be monotonic? Either increasing or decreasing. So what do you think it is? If it is one or the other, which one do you think it is? Increasing, you can just tell. 2, and the next one is what, like 2.5, and the next one is like 3.3.3. So it looks like this is getting bigger and bigger, right? But you have to show it algebraically, and that's the part of this that can be a little messy. My claim is that it is increasing. In other words, I want to show, which from now on I'll just write WTS whenever I want to say I want to show. WTS, want to show that A sub n is less than or equal to A sub n plus 1. That's what it would mean. That's what increasing means, right? The nth one is always smaller than the next one. Or you could say the next one's always bigger than the previous one. So now what we're going to do is we're going to work with this inequality, and we're going to see if we come up with a true statement at the end. So plug n into the sequence, or write down the sequence, which was this, n over n plus 1 over n. I'm claiming that that is less than or equal to, what is A sub n plus 1? So plug n plus 1 into the sequence. It'd be n plus 1 plus what? 1 over n plus 1. So you see, all I'm doing is replacing the n with n plus 1 in the original sequence. So this is what happens when you plug n into the sequence. This is what happens when you plug n plus 1 in. Now, we have to show algebraically that this inequality is true. How about, yeah, just do some basic algebra first. How about subtracting an n on both sides, and we get that? And so we have this, 1 over n less than or equal to 1 plus 1 over n plus 1. Do you think that's true? Yeah? What you're ideally trying to get to here is a statement that nobody in here is going to argue with you about. Like, well, I don't know about that. It's got to be something so obvious that, you know, someone in college algebra would agree, yes, that's true. This, to me, is still a little bit too messy. So what I'm going to do is I'm going to work with this inequality. I'm going to clear all the fractions. I'm going to multiply everything by the LCD. Just try and get a better thing to work with. So what is the LCD that I would multiply by? Got it right there? Multiply everything by that. So multiply this on top, the ends cancel, you get n plus 1 over here. Then you get n times n plus 1. That's what you get when you multiply 1 times the LCD. And then what do you get here? Just n. Again, subtracting some things. You get that? I'm going to distribute through here. Is that true? I think at that point, we could all say that's true. Because what's the smallest n could be? 1, and when you look at the right side, 1 squared plus 1, that's 2, right? 2 is bigger than 1. And then after that, your n's are just going to keep getting bigger. So it's always going to be bigger than 1. So at this point, I think we can say, yep, this is good. So it is monotonic? Yes? Answer here, yes. It is monotonic. Find the limit. This is going to be our last problem. We'll take a break. Of this sequence. So I'm going to list these out as a list. Root 2, root 2 plus root 2, or multiplication, not addition. That would be very hard. Root 2, 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 dot, dot, dot. You get the idea of what the sequence is doing? Root 2, then root 2, root 2, and then the square root of 2, root 2, root 2, and keep doing that. So keep on kind of adding another root 2 on the outside of it or on the inside. You can look at it both ways. So this looks a lot worse than it is. Now, you don't want to break your calculator out and start doing this. You agree with that? How could I rewrite the next one using powers? Could I do that? So let's see. The square root on the outside of everything is this 1/2 power out here, right? So this root right here is this stuff. And then you have 2 here, and then the square root of 2 is another 2 to the half right there. But then all of that's raised to the 1/2. How could I write the next one out? 1/2, and then 2, and then what? Yeah, I'll need a parentheses though, right? Do y'all see this or not? It starts to get a little bit confusing, but you're trying to account for all the roots. There's this root, and then this root right here is this one. And then, of course, the root that's on that 2 right there is just that one right there. Do y'all see it? And then the next one we could write out. Maybe we might need it, we might not. Let's just see. I'm going to rewrite this again. This is 2 to the half, right? This one is, what's 2 times 2 to the half? When you multiply those, what do you do with their exponents? You add them. There's a 1 right there, right? So 1 plus a half is 3/2. So this is really 2 to the 3/2 right here. Raise that to the 1/2. So you're taking 2 to the 3/2 and you're raising it to the 1/2. What happens when you do something to a power? Multiply. So this becomes 2 to the 3/4. Yeah? Got it? What about the next one? What do you say we take our break? Let's say we'll continue at 11:05, but I want to see if anyone can also come up with what the next 2 of these are going to be. Right? So in the next 15 minutes, hopefully y'all can figure out what the next 2 pieces of this will be. But take your break now if you like. I'm going to go get something with a lot of caffeine in it. I did real quickly explain that problem over there, over left of this over there, is very simple. And if you want me to explain it to you, I will. And I feel like an idiot, but hey, happens. All right, so what would this next one become? Anyone have it? Anyone get the whole thing here? What do you think it is? 2 to the what? 7/8. Anyone agree? Yes? Anyone get the next one? 15/16. Starting to see a little pattern in here? So remember how I was telling you to come up with a formula for a sequence? What would the formula for this sequence be? It's always 2. And then the first one needs to be 1/2, the next one 3/4, the next one 7/8, and then 15/16. Do we recognize these numbers? 1, 3, 7, 15? Those aren't just the odds, right? If it was like 1, 3, 5, 7, 9, 11, then that would be odds. 2, 4, 8, 16? You recognize that? What is that? Those are powers of 2, aren't they? This is 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth power, isn't it? So would you agree that I have a fraction up here? The denominator looks like it's 2 to the n. Agreed? And the numerator always appears to be what? 1 less than that, right? 1 less than that. So could I write 2 to the n, then take away 1. Do you all agree? All right, so let me rewrite this. It's 2 raised to the 2n minus 1 over 2 to the n. What was it asking, though? Find the limit of this sequence. That means it converges. You just need to figure out what it is converging to. So let n go to infinity. What is the limit as n goes to infinity of 2 raised to the 2 to the n minus 1 over 2 to the n? So tell me what's happening right here when n goes to infinity on the top and bottom. What are you getting? Infinity over infinity? So you could get into L'Hopital's rule and you can mess with that, but I think you might be better served to just split this into 2 fractions, right? There's one term on the bottom, so split it up. Isn't this 2 to the n over 2 to the n minus 1 over 2 to the n? But isn't that just 1 minus 1 over 2 to the n? And what happens to this as n goes to infinity? You just get, this is over infinity, that's 0, and you just get 1. So this whole exponent is turning into 1 as you go to infinity. So the limit is what? 2. The limit is 2. That's an interesting problem. There's a lot that you have to be able to do here. I mean, you have to be able to translate this into the exponents, and then the exponents, you got to work those into this. Then you got to see the pattern in the exponents. All right, let me give you some homework. This will be what you should probably look at for the test, which is on Tuesday. This will be the last bit of material that'll be on the test. So I gave you last time 5 through 8 on page 434. You should take a look at (9) through 31 odds. I'm going to give you a hint on number 31. They give you natural log 2n squared plus 1 minus natural log of n squared plus 1. And they ask you, determine whether the sequence converges or diverges. If it converges, what is its limit? So you're going to let n go to infinity in this thing. What happens to this whole thing right there when n goes to infinity? What does it turn into? Infinity. This one? Infinity. Infinity minus infinity is an indeterminate form. We don't know what that is. So what do you think you should start with on this problem? Combine the logs together. So just remember your property of logs. If you have 2 logs separated by subtraction, you can turn into a single log. You turn it into division inside. Do that first, then go work with the limit, and then you should be able to work something out there. 27 is another one that you might need a little guidance with. A sub n equals 1 plus 2 over n to the n. What would happen as n goes to infinity on that? You get 0 here, right? This is approaching 0. So 1 plus 0 looks like the base of this is approaching 1, right? And then the exponent is approaching what? Infinity. That, again, is an indeterminate form from Cal 1. Because we're saying the base is not 1. It's getting close to 1, right? And the exponent's trying to get huge. So anyone remember how to do something like this? No? So again, this is just to give you a hint. So when you work on this at home, you could call this something like y. Is this limit? Sorry, I put the limit in here. And then do you remember this? Take the natural log on both sides. If you do that, you get why is putting a natural log here valuable? Then you could drop the exponent out in front. And if you drop the exponent out in front, like this, it now becomes n times that. And so what you'll get is infinity times 0. And then you can continue and get it to look like L'Hopital eventually with infinity over infinity or 0 over 0. So see how those work out for you. I believe that I have problems similar to those worked out in my last semester's class lecture videos, if you go look at those. All right, in addition to those problems, 1 through 31, 37 and 39. And that'll do it. All right. That's all that's on the test, but we must keep moving. 8.2 series. So, sorry? You got a paper? A series is the sum of the terms of a sequence. Or let's just say the sum of a sequence. So remember, a sequence was just a list of numbers. That's all it was. Now let's add them up. So here's an example. Let's say we're given the sequence A sub n is equal to this sequence. 1/2, 1/3, 1/4. We would call that a finite sequence, right? Finite sequence. Capital S, which will represent the sum of that sequence, is going to be 1/2 plus 1/3 plus 1/4. This is the sum of the sequence, right? That's the sum of the sequence. And so really this whole thing right here, or I should say the right side of that, is the series of that sequence. But we're not interested in the series for a finite sequence, right? We're more interested in the series for an infinite sequence. So take a look at this example. What if we take A sub n to be equal to 1 over n squared? Find capital S, which will be the sum of that sequence. So it's an infinite sequence, isn't it? Let's list out the sequence. Just write it out. It would be what? Plug in 1, you get 1. Plug in 2, you get 1/4. You plug in 3, you get 1/9, and then 1/16. Right? That's the sequence. That is an infinite sequence, right? The series for that sequence is just adding those up. And the problem is that it never stops, right? So how are you going to add an infinite number of things together? That's the dilemma. And then maybe the more profound question is it even possible for a series of an infinite sequence to actually add up to anything other than infinity? You know, I mean, is it even possible? So what do you think? If I take a list of numbers, and let's say they're all positive numbers, and I add them up forever, is it possible that it's not infinity? Yeah, you think so? Okay. We usually get two different, opinions. One opinion of, oh yeah, sure, it can it can be finite, and the other opinion is no way, because you keep on adding more on top. So how can it be finite, right? So I'll give you a quick example to convince you that it is possible to add something up forever, each thing being positive, and it's still finite. An example of that would be, let's just take 1/3. Does everyone agree 1/3 is a finite number? Okay. Does everyone agree that 1/3 is 0.333 forever? Does everyone agree that 0.33 forever is 3/10 plus 3/100 plus 3/1000 plus 3/10,000 plus, and then keep doing that? Right? Because the first decimal here, 0.3, is 3/10. The next decimal is 3/100. The next one was 3/1000. And that's what that repeating decimal means. Each one of these is a number. Each one of these is positive, and we're adding forever. And what we're saying is if you did that forever, you would get exactly 1/3. So yes, it is very possible to have an infinite series of numbers, right, added together, keep adding them, and never get past something. So before we go any further, we need to get some notation down and some language. So notation. What? Notation. If we're going to do a sum, right, a series is a sum, then we're going to use the sigma, just like we did with integration. Let me do it this way. N equals 1 to m of a sub n. That's what the sigma notation tells us, right? If we say sum, the bottom here is our starting index. It tells us where we need to start. Here, n is 1. We're going to start at 1. We will stop when we get to m. We start out, we replace this n with 1, a sub 1. Add to that, now go to 2, then to 3, then to 4. Stop when you get to m, add them up, you're done. This is a finite series right here. Finite series. Finite meaning we stop at some point. Contrast that with this. This would be a sub 1 plus a sub 2 plus a sub 3, but you don't get to stop. We are interested in this. The reason we're interested in this is because what can you tell me about every finite series? It ends, so it has to add up to a number, right? You've got to stop at some point. If you stop, that's it. That's your answer. But if you never stop, the question is it infinite or not? I showed you that it is possible to add forever and get a number. What I didn't show you is the other side of that. What if I take, I don't know, 1 plus 2 plus 3 forever? Is that finite? Does that add up to be a finite number? No, this is infinite, right? We could say that's infinity, basically. So you could get two different scenarios here. You could get it adds up to be a number, 1/3, or you could have a series add up and become infinite. But if it's a finite series, you're guaranteed that the series converges to a number, that you actually get an answer. All right, so with that, we now want to talk about what are called partial sums. Do they use K? They use N. All right. Given A sub n, so someone gives you a sequence, right? Then we define a new sequence as follows. S sub n equals, we'll do S sub n, equals sum k equals 1 to n of A sub k. So we have to make a distinction here between, well, we have to be very careful in the wording of all this. Somebody gives us a what? What is this right here, A sub n? A sequence, right? This is a sequence. So this is actually like A1, A2, A3, just a list of numbers, right? Someone gives us a list of numbers. I'm now going to define a new list of numbers. And that list of numbers is defined as follows. So if someone gives you a sequence, they have to give you a formula for it, right? And from that formula, I'm coming up with a new sequence, and here is its formula. Its formula is that it is the sum of the first n pieces of the sequence that we're given. So this is really just A sub 1 plus A sub 2 until I get to A sub n. All right, k is my index, so I start at 1, I stop at n. This right here is called the nth partial sum. Let's see why it creates a sequence. Tell me what S sub 1 is. What's S sub 1? So n is 1, right? That means this n is 1. So I'm going to start at 1 and end at 1, right? So that means all I get to do is plug 1 in here, and I'm done. So I get what? S sub 1 would be A sub 1, and that's it. What would S sub 2 be? So now I replace this with 2, which means I'm going to start at 1 and end at, this time, 2. And I add up, right, A sub 1 plus A sub 2. Understand what's happening here? The third partial sum would be A sub 1 plus A sub 2 plus A sub 3. Got it? Fourth one would be add up the first 4. Fifth one, the first 5. And the nth one, we already had it written down up there, is the first n of them, right? That's that nth partial sum we're talking about. So I wanted to show you a picture of what we mean, and so you can see the difference between A sub n and S sub n side by side. This might help you on your homework. This is the sequence sign of n. Look at what the sequence sign of n looks like. Does it converge? No. Does not converge. Okay, so here's an example. Can I make this any bigger? Okay, I have right here, I have a sequence A sub n. It is defined to be n squared over 1 plus n squared. I think we looked at something like that earlier, right? We said that it converged to 1, didn't we? The sequence converged. But look at what the n partial sums do. So if I take the first guy right here, right, S sub 1 would be just this guy right here, wouldn't it? Which is the answer right here. S sub 2 would be taking this guy's height and adding this guy's height to it. Stack them on top of each other. That new height added together is this number. Yes? My third one would be the first 3 stacked on top of one another, and you get this height. And so look at what's happening to the n partial sum. As I go out further, watch, this is going to 1. Look what happens to the n partial sum. What is it going towards right now? 48. The further I go out, what happens to the partial sum? 248. So the more pieces of the sequence I pick up, the bigger this number gets, doesn't it? So even though this sequence converges, its series appears to do what? Goes to infinity. So it diverges. Yes? See the difference? Just because a sequence converges does not mean that its series converges. Now let me show you a different example. 1 over n squared. Here is a sequence that approaches 0. Do you see it? And look at its series. Does that look like it's converging or diverging? Looks like it's converging, doesn't it? I went pretty far out to begin with, but here you can see that sequence right here of the n partial sums looks like it's headed towards something. What's another one I can do? How about a classic? There's another one. All right. This is converging over here. Okay, so what we're going to be interested in doing now is trying to figure out if somebody gives us a sequence, looking at its series and trying to figure out whether or not that converges or not. That's what we want to do. Understand geometrically kind of the idea? Okay, so we have the idea of what an n partial sum is. Now let's define what it means to be convergent and divergent, all right? A series S sub n, we'll write it this way. Sum n equals 1 to infinity a sub n is said to converge to the number capital S, which stands for the sum. That's the sum, right? The series is adding things up. If it adds up to a number, we're going to call it S. So a series is said to is said to converge to the number S if S sub n goes to S. So we will say that the series converges if S sub n goes to S. Remember, S sub n is a sequence, isn't it? A sequence of numbers. If that sequence of numbers gets closer to S, then we say that this series converges. Otherwise, what? It diverges. Is that me? Shit, I meant to turn that crap off. I'm sorry. Someone's missing. I'm kind of making a big... Okay, stop. I was looking at that the other night. I was like, should I take the Amber Alerts off or not? I was like, you know, there's kids. One day it's going to be some kid and, you know, and then interrupts me during class. Great. All right, so when we talk about series and their convergence, we're going to be investigating, everything is going to be really much determined by what's happening in here. We're going to be looking at the sequence and the way the sequence behaves, trying to come up with this capital S, this number that it goes to. What we're going to find out is that a lot of the times, more times than not, we are never going to be able to find S. But what we will be able to do is say that it does converge or it does not. It does or does not. There's only a few cases where we'll actually be able to get S. In our first example, our first important type of series, we will always be able to get S. And it's called the geometric series. So this is our first big series, the geometric series. Okay. Is that me? It's not me this time. See, I'm not the only one that cares about kids, I guess. Did you even read it? I didn't either. For all I said, you know, for all I know, it says that there's some kid missing on our campus on the 3rd floor. Yeah, nah. Who cares about that? Okay, so the geometric series. What does a geometric series look like? Well, here's what it is. Anytime you have an infinite series that looks like A times R, that's an R, to the n minus 1, where A is a constant, R, well, do we really need it to be bigger than 0? See, do they go with that? No, they don't. Good. Okay, so we don't need that. R is a real number. Not 0. Wouldn't make a whole lot of sense if we were to let this number be 0, because then we would just get 0 in there, and if you add 0 up forever, you're still going to get 0. So it would be convergent, but it's really not that important to us. All right, that's what we want to know. That we want to know what that behaves like, what it acts like. So here are some examples of geometric series. Have you ever heard of that example, or I think it's called Zeno's paradox, where they say that like a person can never finish a race. Like if you're running a race, like you can never finish the race, because in order to finish the race, you first have to finish half the race, and then after that you have to go the next halfway, and then you have to go halfway again. And if you keep going halfway, 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 like you can do that forever and never get to the other side. So you can never finish a race because you always have to go halfway each time. It's a paradox. I mean, we all know you can finish a race. But the idea is that if you go half and then half, like trying to go across this room, if we go half the way and then half of that and then half of that and then half of that, like do we ever reach the wall? You understand? So what would it be if we took a half plus if we've gone halfway, what's half of what's left? A quarter, so 1/4, so half of a half. I'm going to write it like that. I know that that's 1/4, but the next part would be half of a half, wouldn't it? Half times a half times a half plus another one, half, 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 half. So this really looks like 1/2 plus 1/4 plus 1/8 plus 1/16 plus, and it keeps going, yes? All right, so what we want to do is somehow try and realize that that's a geometric series. So each of these pieces, 1/2, 1/4, 1/8, 1/16, those are coming from the sequence, remember? The sequence is the piece in here. Somehow I need to connect this formula to these numbers, 1/2, 1/4, 1/8, 1/16. So it might be worth it for me to rewrite this using what they have in common so that I can find a pattern. Do we agree with this? 1/2 is 1/2 to the first power, 1/2 squared, 1/2 cubed, 1/2 to the fourth. And even better than that, I could write 1/2 to the first power, and then I could write 1/2 to the second power, and then 1/2 to the third power, and then 1/2 to the fourth power, right? Plus dot, dot, dot. That keeps going. I forgot to say dot, dot, dot on the other one. So look at the geometric series. Look at what you need for a geometric series. You need to have a number. Get off there. You need to have a number sitting in front of these different powers of R. R is going to be some number. It's always going to stay the same, but the powers on it are going to change. And then some number in front of it that never changes. So do we have something raised to powers and the power keeps changing? Yes? Do we have a number sitting in front of all of these? What number is sitting in front of all of these? 1. So we have a 1, we have a 1, we have a 1, we have a 1, right? And then that makes our best candidate for R to be 1/2, right? Looks like that's our R. That's what it's looking like. It's looking like that's our A and like that's our R. But we need our formula. We need this to work so that when we plug in 1, right? 1 is the first number we plug in. When we plug in 1, we need to get this first guy right here. Right? We need to get this first guy. When we plug in 2, we need to get this guy. So here's how I'm going to approach it. What I'm going to do is I'm going to first write down this series, and I'm going to create this and not even worry about this right now. All right? I'm going to create this. So I know I need to start. I need to have a 1 out here. I actually don't need to write it, but I'm writing it just because it's our first example. I know that this is 1/2. And I know that my first power that I ever get on that 1/2 needs to be a 1, right? Needs to be a 1. And it just so happens I'm starting at 1, right? So how about just putting n up here? Would this right here create this? Would it? Let n be 1, what do you get? 1/2. Plus, now let n be 2. 1/4. Next one. So this would create this, yes? But does this look like this? What's the difference? In order for this formula to work, your index has to start at 1, which ours does, but this has to be an n minus 1. And ours is not an n minus 1, it's an n, right? So what I'm going to do now is what we've done in the past whenever we wanted something to happen that wasn't there. Remember, we like just made it appear. I'm going to just not put the 1 out there anymore. What do I really want up there? N minus 1. So I'm going to take it and I'm going to minus and plus at the same time. Take the n that was there, subtract and add 1. If I subtract 1 and add 1, that's still n, so I haven't changed the problem. But now what that allows me to do is rewrite it this way. Now things have changed a little bit. I do have an r, right? I do have an r. I do have the n minus 1 that I need in the formula, right? My index is starting at n equals 1, just like in the formula. But I thought a was 1. But after I massaged this thing and forced that exponent to become the n minus 1, I actually realized that the a is what? 1/2. All we've done is I started with this geometric idea of going halfway, 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 and I've shown that if you can rewrite everything, you can realize that that whole concept of that problem turns into this geometric series. And the question is, does it converge? What do you think it's going to converge to if you think it's going to converge? 1, right? Because the distance across the room should be 1 unit, whatever it is. Halfway, then half. Now we have to show that it is 1. And for geometric series, the thing is, you don't have to keep on doing the proof of it every time. We just do the proof 1 time, and then we use the formula, and we're in business from here on out. So, but we have to prove where it comes from. So here we go. Question is, what is that? So we stop that. We'll come back and answer that in a second. This is a very loose proof, okay? I'm not claiming that this is in any way like a real mathematician would write a proof, but I think it'll suffice for this class. The question now, what does that add up to be? So here's what we're going to do. We are going to first start by looking at the nth partial sum. What is S sub n? By the definition, what's S sub n? Sum k equals 1 to n of a sub k, right? So remember that the series, right? The series, from the series you can create these sequence of numbers. I'm looking at the nth one. So I'm stopping my sum somewhere. This, for us, in this problem, our a sub k is that entire expression right there. So can you tell me what S sub n is? Plug in 1 into this. What do you get when you plug 1 into this for the n? Yep, you get 1 minus 1 is 0, r to the 0 is 1, so you just get a. A plus, now plug in 2. Plug 2 into this. AR. Plug in 3 into this. Plus AR squared. Plus AR cubed. When do you stop? AR to the n minus 1, right? Because when you stop, you plug in n, right? I'm doing the n partial sum. So I'm stopping it at n. If I plug n in here for n, I get n minus 1. So everyone agree that that's what we're trying to find the nth partial sum? And then I want to remind you of the definition because I don't want you to lose sight of this. Remember this little subtle thing right here that said that a series converges to some number if the nth partial sum goes to s. Remember that this means limit n goes to infinity of s sub n. Isn't that what that means right there? That this would be equal to s? Yes? They find them? No, something different. So I'm writing down the definition of s sub n because I want to know what happens as n goes to infinity, right? Tell me real quickly if you know what happens when n goes to infinity right now, because it's not going to tell you shit, really. As n goes to infinity, this just gets longer, right? The chain just gets longer? Yes? Okay. So here's where we do something extremely clever, and I didn't make it up, someone else did this, all right? So watch this. It doesn't seem like a natural move, but I'm going to multiply both sides of this equation by r. Just do it. See what happens. R s sub n. Agreed? What happens on the right side? AR plus AR squared plus AR cubed. And that'll keep going on until I get to the very end. What would happen if I multiply this last one by an r? AR to the n, right? Because you're going to add 1 to that exponent. N minus 1, you're going to add 1. And so you'll get just AR. So again, don't worry yourself with, well, how would I have ever known to do that? Just, do you agree if we do that, it'll work? Yes? I forgot to put the n. Sorry. My fault. All right, so if you agree that this line is correct, that's just by the definition of what s sub n means, and you agree that multiplying both sides of that equation gives you this, then tell me what this is. What's s sub n minus r s sub n? So take this s sub n and subtract from it this. So a, take away, there's no a's here, right? I can't just take away an a. How about AR? I'm going to take away, do I have AR here? Yes. So this one would cancel with this one. AR squared, take away that AR squared. AR cubed, take away that AR cubed. And we do that all the way down here. How about AR to the n minus 1? Is it going to go away? Yes, because isn't it right here? Right here, isn't it AR to the n minus 1? The one right in front of this one is AR to the n minus 1. So it will cancel with this. Now, is there anything left to cancel this one out? No? Right? There's nothing over here to cancel this one out? So what you'll be left with is this A. And then remember we were subtracting minus this right here. You following me? All right. So if you agree with this, I'm gonna go back and remind you what we're interested in. We're interested in figuring out what happens to s sub n as we let n go to infinity, right? That's what we're interested in. And we said up here that if you just wrote this and let n go to infinity, it just gets longer, so that didn't help. We did this weird thing and then subtracted them. Why? I don't know. And somehow it's going to get us there. On the left side, what do these both have in common? Sn. S sub n, pull it out. Factor it. Good old factoring, right? Can you solve for s sub n now? Yeah. Divide both sides by 1 minus r. And look at this formula for S sub n now. Remember, the formula we had before for S sub n was a bunch of things added up until I got to this last one, right? So if I let n get bigger, it added more junk to this. Compare that to this equation, which is represents the same sum. According to this, it's just whatever this is. What happens as n gets bigger now? Do we add more junk to this in this expression? All that happens is this one is affected, right? What happens to r to the n as n gets big? It'll depend on r, won't it? Now, we did that earlier today. We said, yeah, was it right here? Yes, it was this. Remember I said this can be an important sequence. If you have r to the n, if that r is bigger than or equal to 1, it's going to become infinite. If that r is between 0 and 1, it's going to go to 0. And we need that right now because we want to know what happens now. What is the limit as n goes to infinity of S sub n, which is the limit as n goes to infinity of a minus ar to the n over 1 minus r. So we're going to have a couple of cases here, right, of what's going to happen. This will be equal to, now here are my two cases. Let's start with this one. If r is bigger than or equal to, let's say bigger than 1. What happens here if r is bigger than 1? This is a negative, right? But what happens to this piece right here? If it's bigger than 1, it's going to go to infinity, right? And that means your numerator is going to blow up. And your denominator is just going to be sitting there at the same number the whole time. So that becomes infinite, doesn't it? And that's going to diverge. So if the r is bigger than 1, this is a divergent. It's a divergent series. The geometric series diverges. What might help you see that is if you go back to this right here was what a geometric series was. If you write these out, I didn't write them, but it was a plus ar squared plus ar cubed forever, right? That's what this geometric series means. If this number is bigger than 1, like let's just take 2, then this would be a plus 2a plus 4a plus 8a. If you keep adding these up forever and a is fixed, that thing's going to get huge. So it diverges. But what if r is less than 1? Or, yeah, if r is less than 1. So if that number is less than 1, this thing goes to 0, doesn't it? And then all that's left is the a right here over whatever 1 minus r is. Because that piece goes away. Well, this whole term right here goes away. Y'all see that? Now, to save us some time, it can be shown. I'm not going to get into it because it gets a little bit tricky. Is that if you put absolute values around these, and also add an equal sign right here, that it takes care of all the negative r's also. So if the magnitude or the absolute value of r is bigger than or equal to 1, it's going to diverge. If the magnitude of r is less than 1, it's going to converge. And it's going to converge to this number. So getting back to the problem we stopped at. We stopped here, right? We said this is geometric. We know what A is. We know what R is. So now I'm going to list them out even more explicitly. A is 1/2. R is 1/2. The first thing you have to question yourself about here is the value of R. What is the absolute value of R here? Just 1/2, right? Is that less than 1? Yes. Because it's less than 1, this converges. What does it converge to? So therefore, S equals A over 1 minus R, which for us is A, 1/2, over 1 minus 1/2, which is 1/2 over 1/2, which is 1. Which is what we said we thought it would converge to. I'm going to do another one. Did you all get that? You need it? No? Anyone still need it? Where is it? Anyone still need that? Find this sum. So be real careful with this, because now we're looking at an infinite series, right? This is an infinite series. We are not just taking the limit and letting n go to infinity. That's not what this is about anymore. I mean, it will be something we look at later, but it's not as simple as that. It's not going, oh, okay, as n goes to infinity, this is infinite, that's becoming infinite, oh, L'Hopital's rule. It's not that. We're trying to find a sum, right? If I tell you, find the sum, that means it can be found. That means that it converges. That's a hint on a test. If I say find the sum, you know it converges. You just actually have to figure out what it is. And that's a good thing, because it narrows down what it is you could possibly do. Right now, the only series we know how to find this sum of is a geometric. It's the only thing we know. So in some way, shape, or form, I'm telling you this is a geometric series. You have to now make it look like a geometric series. So what are the conditions we need for a geometric series? Well, our index has to start at 1, right? So our index does start at 1. We're good with that. Now what we need is an A, and then an R, and then n minus 1 in the exponent, don't we? I don't have n minus 1 in any of these things, do I? So I'm going to force an n minus 1 into all of them. So now I begin rewriting it. I'm going to make 5 to the n plus 2 of 5 to the n minus 1 plus 1, but I still had plus 2 up there. I'm going to do pi to the n. I'm going to take away 1 and add 1. Then I'm going to do 3 to the n. I'm going to take away 1 and add 1. But I already had 1 there, so plus 1 still. All of this is because I want the n minus 1 powers on my numbers here. Still rewriting. 5. What happens when I put the 1 and 2 together? I get 3, right? So I could write this as a 5 cubed times 5 to the n minus 1. Do you all agree with that? It's the same thing. And then on the bottom, let's do the same thing with the pi. I can write this as a pi times a pi to the n minus 1. And then times, what about the 3? How can I write that? 3 squared times 3 to the n minus 1. I'm just going to highlight real quick. These are the things that are all raised to the same power, aren't they? Everything else is just numbers. 125 on top, 9 pi on the bottom. Yes? So here's where I'm at. N equals 1 to infinity. I've got 125 over 9 pi times. Now, since all of these numbers are all raised to the same power, I could also write the whole expression like this. Is that not the same thing? 5 to the n minus 1 on top, so 5, and then here's my n minus 1 power would be applied to that. Pi to the n minus 1, 3 to the n minus 1, put those two together, that's 3 pi to the n minus 1. Questions? Are we there? Do you see an A and an R? Yes? Here's your A. Here's your R. This is only going to converge if the absolute value of R is less than 1. What is the absolute value of R? The absolute value of 5 over 3 pi? Well, pi is about 3. 3 times 3 is 9. 5 ninths, I mean, this is smaller than 5 ninths, so it's definitely less than 1, isn't it? Check. That means it converges. What if that was greater than 1? Diverges, done. But it doesn't. It's convergent, so therefore the sum, capital S, will be equal to A over 1 minus R, which for us, A is 125 over 9 pi over 1 minus R, but R is 5 over 3 pi. And that's the exact answer. You could clean this up, get common denominators, flip things around. I just wouldn't take it to a decimal, because we're not asking for a decimal, we're asking for the exact answer. So that's it for that. The original? All right, I'm going to do another one. This one is going to be a little more interesting, I think. I hope you'll enjoy it. All right, what we have here is an equilateral triangle. Yes, equilateral. What does equilateral mean? Equal lengths, right? All the sides are the same length. Imagine coming in here and putting a circle in here. Terrible circle, but you get the idea. And that circle touches tangent to all sides, right? And then from there, you draw another circle that touches tangent here, tangent there, and back up like that. And then you do the same thing. It's going to touch tangent, tangent, and then tangent to that circle. And then you do it again, tangent, tangent to that circle. And you do it again, tangent, tangent to that circle. And you do that forever. You could do that forever, right? I mean, theoretically. But you also do it in the other directions. So like you would have had the same thing over here, same thing over here, same thing over here, same thing here, same thing here. Yes? All right. Let's just call this we want to say the side of this here, let's say it has length 1. Find the total area occupied by all the circles. All infinitely many of them. What's the total area? Find area of the blue circles. Okay, it's 12:10. We go to what, 12:30? All right. So let's see how much of this y'all can do in groups. I want to see if any group can get this problem. I'll give you a hint. It turns into a geometric series. But you got to come up with the formula for it. Start drawing pictures because you're going to need to draw pictures, right? I'll give you another hint. The center of this circle, right, is also kind of the center of the triangle, isn't it? Because it's equilateral. I know the way I drew my picture, it doesn't look that way, but so what I would do is first try and find a formula for the area of this circle. Somehow, some way, try and then find the area of this circle or a formula for it, and then the area of this circle. And if you do it, you'll start to see that each one of them has, as you move through them, there's a pattern to the areas, and from it you can create a geometric series. Okay?